So in this video, I'm gonna show you how to work with files in Linux on binary level. As you probably already know, computer fundamentally understands data in binary representation. It means in form of zeros and ones, unlike us humans who are used to work with decimal numbering system, which includes digits from 0 to 9. But we want our computers to be able to work with human-readable text, right? So let's get started. I want to make this video pretty practical. Let's create some sample file with simple content, like this hello string. So I used echo to output it to test.txt, and now we are reading it with cat. And as you can see, this string was successfully written to this file. But what if I want to see the binary content that is stored in this file? So we won't start with zeros and ones, although we will get to this. Let's first use the hexdump tool to show the hexadecimal representation. Hexadecimal system, as name implies, has 16 digits. First 10 is just regular decimal ones, 0 to 9, and the 6 other ones are A to F. As you can see in this representation, in the left column we have the address in this file. In the middle column we have the data in hexadecimal form, and in the right column we have data displayed as regular text, ASCII text. In this output, each group of 2 symbols represents roughly 1 character, 1 symbol, 1 byte. But as you have seen before, we have printed a word of 5 characters, but here we have 6 bytes. So what's going on here? We have printable characters like H, E, L, O, but also we have unprinted characters, like for example spaces, tabs, new lines, line feeds, some control characters like backspace, etc. We can see this here as well. So when I printed this test.txt file, you see hello string, but also you may not realize this, but terminal also have interpreted the new line character, and that's why the next command starts from new line. We actually can test this. So I can print hello and it prints on separate line, and then we get the new line for our new command. But echo actually has the flag n, which suppresses it from printing the new line character. And here we have hello, and the prompt for the next command starts right away without a new line character. So this is the first benefit that we get from examining the files in this binary format. We can see these unprinted characters. In this representation, new line is printed as 0A, and on the right you can see it is represented by a dot. So dot means just any unprinted character. But how do we actually know which byte corresponds to which character? So for example, that letter H is represented by 68 in hexadecimal, letter E by 65, and so on and so on. So there is this thing called ASCII table. It contains 128 characters. Here it's divided in 4 columns, each of which has 32 characters. And here you can see different representations of each character. So dec means decimal, hx means hexadecimal, oct means octal, char means the character itself. It can be printable, and if it's printable you can see the character right away, for example 0, 1, 2, 3, ABC, and so on. If it's not printable, you can see how it's called. For example, the tab character, which is number 9 in decimal here. So you can also see this character 0a, which represents line feed or new line character basically. And it's also in this table under decimal number 10. And you can see it's A here as well. And let's verify that this hex dump output is actually correct. So let's take this 68 byte and find this in this table. You can see it in the last column, and yeah, it's indeed the H character. Let's take 65. It's here as well. And the last character, as I've already shown, it's a line feed character. And actually new line is represented differently in Windows and Linux. In Linux it's just LF character, byte 10, while in Windows it's CRLF, which is bytes 13 and 10. It is this way due to historical reasons. There is a command similar to hexdump, it's OD, which means octal dump. By default it prints in octal, which means it uses digits from 0 to 7, but it can also produce output similar to hexdump. Although, if you compare the two, you can see a slight difference. So in hexdump we have 68, then 65, but here we have 65 and then 68. And you can verify by ASCII table that byte 68 should be first, which means letter H, and then should follow letter E, 65, and not the other way around. The reason that OD prints it this way is this thing called endianness. Here I've brought up the Wikipedia article about this concept, so it's basically about byte order. In little endian order, the least significant bit goes first, and in big endian, the most significant bit goes first. The order which aligns with how would you read the English text is big endian, although the physical data might be stored in little endian format. So you need to know which format do you see and interpret it accordingly. Usually we don't inspect regular text files in this way, because we can just view them in regular text editor, and this way is often used for binary files. You can inspect any binary file in this way that you have on the system. So you can, for example, look in /bin directory. I will choose ls. So let's do a hex dump of bin ls. As you can see, it's a pretty big dump. A lot of data here. Some of it is readable, so you can understand some words here, like property, node, GNU build, etc. But usually it's unreadable, or it's some random characters, because it's binary file, it's compiled and ready to be executed on the computer, but not meant for humans to read. What is also interesting here is this star over here and over here, and there are such stars in other places in this output. So what it means is actually omitted empty lines. So if there are several lines with just zeros, hexdump omits them and prints this star instead. You can change this behavior by using vflag. It will make hexdump print the entire file, and also those places where there are only the zeros, like here, for example. Let's say you want to edit this file and you want to do something unusual, like, for example, delete the training new line in this file. I will open this file in Vim, in my case NeoVim. Usually it's not easy to do such things, because as you can see, I only see the letters here and I don't see new line. I cannot just delete this. For this I want to create some bigger file. For example, let's do listing of / directory. I will place it in ls.txt file. Usually Vim comes pre-installed with XXD utility, so let's see its man page. XXD, make a hex dump or do the reverse. This is what we need here. Let's see this utility in action. So by default, it just prints the hex dump of file in this colorful output, but it can also reverse the hex dump. So let's first store it. I will redirect its output into xxd.txt. Let's see the output. Yeah, it's stored in the file. And let's now do the reverse. For this, I will pipe the cat output to xxd-r, and it will reverse. This R flag is for reversing the output. And you can see we get our listing back. We can use this concept for editing, but before this I also want to show another flag of XXD, which is P. Let's do this on our ls file, and you can see it's just plain hex dump without any ASCII characters. Let's open our ls.txt file in new Vim. If we want to edit this file in hex format, we first need to convert all of these lines to hex dump representation. For this, let's run vim command using colon, then %, exclamation mark, and then xxd, and then p flag. And as you can see, all of file content was replaced by hex representation. So what does this vim command mean? % means work on every line of our file. Exclamation mark means run external command. And after exclamation mark, we have the command itself, which is xxd-p, which I have shown you before. So basically this command filters every line in our file. Now let's say you for some reason want to delete trailing new line in this file. Let's go to the end of this file and delete this 0a sequence, which, as we have seen before, is denoting the new line character. And now we need to convert this back. Let's do similar sequence. So we're using % for all lines, exclamation mark for external command, and then xxd, r reverse, and -p flag. And notice that you need to use r and p separately. Don't do this because it won't work for some reason. I don't know why. And we get our ls output back. Let's save it now using :wq. And let's see the hex dump of ls.txt now. And you can see that we still have this 0a byte at the end. By the way, notice two interesting things. In the end, we have 000a. But it doesn't actually mean that we have byte 0 and byte a in the end of this file. It's just hex dump filling the second byte with 0. This is default output of hex dump without using the -c argument, and also actually it uses reverse byte format. I mean little endian format, which I've talked about before. And before 000a, we have 7261. And now let's compare this to traditional hex dump output. Let's put flag -c before this. And you see it's 6172. So it's big endian order. And also you can see that we have just 0a here. We don't have 0a00. This is what really appears to be in the file. It doesn't contain that 00 byte. But now let's try to fix the fact that Vim doesn't allow us to remove trailing new line. Let's open ls.txt again, and we need to set several options here. So first let's do colon set binary, and then colon set no fix end of line, no fix EOL. And it should allow us to do what we want to do. Now let's do colon %, exclamation mark, xxd dash p, and we still see 0a at the end. Let's remove it and turn this back into normal representation with %, exclamation mark. And now let's convert this back to plain ASCII text representation with colon %, exclamation mark, xxd dash r dash p. We cannot verify here that there is no new line at the end, but we can save the file with colon WQ, and let's do now hexdamp-c ls.txt. And as you can see, there is no 0a byte at the end. And if you try to do cat on this file, you can see prompt appears on the same line where output also appears. You can also use regular hexdump for editing, which includes ASCII characters and not just hex only dump. For example, let's do this again. Now let's edit this dump. I want to remove this 0a and find byte for exclamation mark. As you can see, it should be hex 21. Let's put it here. And also I want to add some digits, like for example 0, 1, 2, 3, and 4. Let's do reverse xxd-r, and we have string hello 0, 1, 2, 3, 4. Let's save it, and here it is. But editing in this way might be problematic because yeah, it looks better than just plain dump, but you need to make sure that edits you make will be readable by xxd-r. And if you produce wrong input, you may get wrong result or just error. This ASCII table might seem confusing, but actually it's pretty logically constructed. I can show how convenient the ASCII table actually is by using the bash feature to expand all digits from 0 to 9, like this. And let's remove the space between the digits, and now let's do the hex dump. As digits go from 0 all the way to 9, ASCII representation conveniently goes in the same way from 3.0 all the way to 3.9. Now let's do the same for small letters. They essentially start from 6.0, but the first letter is 6.1, and they all go consecutively. And let's do the same for big letters. They go from 4.1 and above. We can also construct files in hexadecimal format by hand. So for example, let's use echo to print first 5 letters. So as I already said, small letters start after byte 60. So first will be 6.1, the second is 6.2, 6.3, 6.4, and 6.5. And I put \x before each byte to denote that this is a hex representation. If I run this command, it will just print it by itself and don't convert it to bytes. But echo can interpret the escape sequences and \x and then 2 digits, it's actually an escape sequence, and echo understands these sequences. To do this, we can put flag E to echo, and now we see A, B, C, D, E. But also echo prints new line at the end. If you want to avoid this, you can put argument n to it. Let's now add a new line to this. So I will place \x 0a, and now let's print first 5 digits. So this will be /x 30, 31, 32, 33, 34. It might be actually better if I leave that new line. Let's now talk about Unicode. As you can see, this ASCII table has only 127 symbols. It contains English alphabet, digits, some control characters, some spacing characters like space, tab, but there are many other characters that are used throughout the world, for example Chinese, Japanese, Korean script, Cyrillics, and many other symbols. Clearly 7 bits or 128 possibilities are not enough to represent all of that variety. And thus there is another standard to do this. Enter Unicode. Right now it has this many characters, above 100,000 of them. Here you can see the list of them, and notice that first symbols are exactly the same as in regular ASCII table, because Unicode is meant to be backwards compatible with ASCII. ASCII ends with symbol 7F, and you can also see it in Unicode table. But after that, there are many other symbols that are supported by Unicode. Now let's do some testing. As I have said before, you can print ASCII symbols using /x sequence. For example, let's print digit 5. As you can see, before the next prompt there is digit 5 over here. Let's do a hex dump of this digit. So I'm piping the output of echo to hex dump. And notice that I use echo with NE flags. N means that we don't want to print trailing new line, and E means that we want to interpret the escape sequences, like this \x sequence. As you can see, we have byte 3, 5, and we have 5 shown on the ASCII representation column. We can also see this directly in binary using XXD tool. Here you can see binary representation of this byte. It has 8 bits because 1 byte is 8 bits. Now let's test the limits of this. Let's print the byte which contains all 0 bits. It is called the null byte. Here you can see we have all zeros. Let's print the maximum byte, which is FF byte, which will have all ones. And here it is. Now let's print the maximum byte from the ASCII table. It's 7F byte. As you can see, we have 0 and then all ones, because we use all 7 bits and they are equal to 1, and the first bit is equal to 0. And this is an unprinted character. As you can see, it's represented just by this dot. Now, what if we want to print some other character other than from ASCII table? We need to open the Unicode table, and let's choose some character from it. Let's choose this Greek omega letter. It has Unicode code point of 03A9. How we can use it? We can use it by changing the escape sequence. Now we need to use not \x, but \u, which stands for Unicode 03A9. And you see the binary representation of it. And on the right side, we don't see the omega letter because these tools like XXD and HexDump, they only show you the ASCII encoding. So we will not see the non-ASCII characters here. But if I just output this symbol to the terminal, you can see the omega right before the next prompt. Now let's look at how it's encoded. As you can see, we have not single, but we have 2 bytes over here. And in binary representation, you can see 2 groups of 8 bits. And also, you can notice some discrepancy here. We see \u 03A9 in Unicode code point, but here we see CE-A9, so it looks a bit differently. Why is this? It's because Unicode standard specifies just the mapping between symbols and their Unicode code points. So code point is basically this string over here. It's basically a number, an ordered position of character in Unicode table. So Unicode basically says that letter omega corresponds to 03A9 code point. But it doesn't say how this symbol should be represented in terms of actual bytes. And as you can see, actual bytes that represent this symbol is CE-A9 here. And which bytes will represent the Unicode character will depend on encoding. And the most popular encoding that is widely used in the web and other applications is UTF-8. Here is the Wikipedia article about UTF-8 encoding. And what I want to show is this table with mapping from Unicode code points to UTF-8 representations of them. This first row represents regular ASCII characters. It starts with code point 0 and ends with code point 7F, which is exactly the range for ASCII characters, as you can see here. So if UTF-8 sees that byte starts with 0, it automatically understands that this byte represents an ASCII character. But if we want to represent non-ASCII characters, we will look to these following rows. If UTF-8 sees that byte starts with 110, it understands that it is the beginning of 2-byte Unicode character. How do we know it's 2? How do we know that it will be 2-byte character? Because it starts with 2 ones. This is the convention. If you look at third row, the first byte starts with 3 ones. If you look at fourth row, it starts with 4 ones. And the subsequent bytes starts with 10. And this is the same for the next row. 10 here, 10 here, and here, and here, and here. Now look at our case. As you can see, the first byte starts with 110. So we have 2 ones. That means we understand that there are gonna be 2 bytes representing a 2-byte Unicode character. And the second byte starts with 10. It means that we have continuation of Unicode character, which started in the previous byte. So for actual data, for actual Unicode code point representation, these bits marked as X are used. So in 1-byte case, we have 7 bits of data. In 2-byte case, we have 5 bits here and 6 bits here, total of 11 bits, and so on. Now let's print some more complicated Unicode character. So here are emojis, and Let's print this first one, 1F600. And we don't see emoji over here. And here we need to use capital letter U instead of small letter u, because we will use more than 4 hexadecimal digits. And here it is. Now let's look at dumps of this character. As you can see, this emoji is represented by 4 bytes, and the first byte starts with 4 ones followed by 0, which means that we will have 4 bytes in total for this character, and the following bytes all start with 1, 0. And that's about it. If you found this video interesting and useful, please consider liking it and subscribing to my channel. The war in Ukraine continues, so please consider donating to Ukrainian defenders to help fend off the aggression. You can do this by donating to Come Back Alive Foundation, link in the description, or by any other valid method that you find.